This presentation is on foundations. So an overview of foundations. We'll take a look at loads and settlements of foundations, safe foundations, the types of soil that make up the foundation and their properties, the properties of foundations, good foundations that is, strength, stability, drainage, etc., some estimating and soil properties, exploration and testing, and the construction of foundations, type of soil layers at the top, excavation support for soil, soil strengthening and dewatering. Then the types of foundations, shallow and deep, and what's called the influence zone. Some precautions on seismic base isolation, underpinning during construction, and retaining walls, waterproofing, drainage, reinforcing and insulation, frost protection, foundation design for optimal cost. So a function of a foundation is to transfer the structural loads from a building safely into the ground. A backyard tool shed may need only wooden skids to spread its load across an area of ground surface, whereas a house would need a greater stability and consequently its foundation should reach the underlying soil that is free of organic matter and unreachable by the winter's frost. A large and heavier building of masonry, steel, or concrete would require its foundation to go deeper into the earth, such that the soil or the rock on which it is founded is competent to carry its massive loads. On some sites, this means going 100 feet or more below the surface. Because of the variety of soil, rock, and water conditions that are encountered below the surface of the ground and the unique demands that many buildings make upon the foundations, foundation design is a highly specialized field of geotechnical engineering. So load and settlements of foundations. Well, the types of loads on foundations, and we can break that down into dead loads and live loads, wind loads, inclined thrusts and uplift, the water table, and earthquake forces. And types of settlements. Well, there are two types, uniform and differential. Differential settlement must be minimized and depends on the soil condition and distribution of loads on the columns supporting the building. And the requirements of a safe foundation? Well, structure foundation systems safe against settlements that would lead to collapse need to be in place. And foundation settlements should not damage the structure, and the foundation must be technically and economically feasible at the same time. So a little bit about foundation loads, the dead load, live load, and the wind load, along with the horizontal pressures grade, structural member forces, and uplift, along with the earthquake or seismic conditions. Here's a look at what happens if the loads, or if the ground was to shift. The drawing on the right can resemble what a building can end up looking like because the foundations were not put in properly, or with the proper sizing, or of the proper technique. You see the same in a patio, how this settling can be a real problem and cause even cracking in a little item like this type of brick veneer type of flooring or patio type item. So types of soils and characteristics, well, rocks and soils, that's rocks broken into regular and irregular sizes by joints. Soils are usually particulate earth material. And boulders, well, they're too large to be lifted by hands. We know that is a different terminology used in soil. It doesn't mean the large extreme boulders, but anything that's just too large to be lifted by hands. Cobble is another one, which is a particle that can be lifted by a single hand. Gravel aggregates are coarse-grained particles larger than 6.4 millimeter. Sand, frictional size, and it varies from 6.4 to 0.6 millimeter. And to give an idea of 6.4 millimeter or 0.6, let's say 0.6 millimeter, which is a half a millimeter, which is less than a 1/16 of an inch, whereas that's really 6 centimeters or 6 millimeters 0.4, which is pretty much about the size of 3/8. So then there's the silts that vary in size from 0.6 to 0.002, which are much finer, much smaller, almost too small to see with the naked eye. And the clays, which is cohesive fine-grained and has a high surface area to volume ratio, with a size even less than 0.002 millimeter, way outside the range of what the eye can see. And then peat, what is called peat, but that's totally organic, and then those are soils not suitable by foundations. And this is the classifications according to the Unified Soil Classification System. A little bit of what these look like just by the eye. The porous sandy on the top left there. How clays are obviously defined by their red color gives a good idea of what they look like. So what are the properties of a foundation? Well, strength, the load-bearing capabilities. Now, crystalline rocks, which will support about 12,000 psf, and sedimentary rocks a little bit less, at 6,000 psf. And other types of soils, any of the soils are in the 2 to 3,000 range. Now, soils are fine to build on. It's just that anything above 3,000 psf is already exemplary because it's so solid, and that's why the solid rocks can carry high volumes of weight with no problem whatsoever. But the 2 to 3,000 range is fine too. So the thing is that they need to be stable under loads, the foundations, that they don't have any creep or shrinkage and swelling. There's also an item about drainage characteristics. Has to go with the concrete itself about porosity. Porosity, the number of holes, or how porous the concrete is, and permeability, which directly relates to that, because that's water pretty much through a porous foundation. Water is going to be more permeable, able to get from one side to the other. And then a little bit about the soil property estimation, which is pretty much done by subsurface exploration. Test pits that are dug, less than 8 feet deep, borings when it's greater than 8 feet, and then to make estimates of the water table by that, and the testing of soil, those soil samples extracted for various properties such as particle size, distribution, liquid limits, plastic limits, which is called the plasticity of the soil, and water content, permeability, shrinkage and swelling type of items that, or let's say the capabilities or the what happens with the soil is shear and compressive strength, and the consolidation, which has directly related to creep and settlement. So about the construction of footings, some amount of excavation is required for every building. Topsoil consisting of organic matter is removed, and then below the region of soil erosion, that is, by water and wind, and below the level of permafrost, to the required depth at which the bearing capacity necessary for the building is met. That's how the depth of an excavation is decided by all those factors. And a variety of machines are obviously used for excavation. There's a whole item about preventing cave-ins by items or different methodologies called benching and sheeting, for example. Bracing, the idea of dewatering these type of excavations, getting the water out to keep them stable, using well points and sumps, and placing water pipe barriers sometimes to prevent water from seeping into the excavation, and mixing the soil even by rotating paddles. Here's a couple pictures of our different equipment used in creating the foundation work, and a little bit more on the equipment. So what is an unrestricted site? Well, anyway, it has a bench and an angle of repose, must have a perimeter distance. There are different considerations like bank erosion, water diversion, safety, and the storage of the backfill, and these are the most likely and least expensive. So here's a look at a benched excavation. You can see it looks like a series of benches on the earth. You go up a few feet, then horizontal a few feet, keeping it flat, kind of like terraces. And the idea is these are used in mostly sandy soil. There's quite a degree of angle there, maybe a 40. There really ends up being a more than a 45-degree angle, and the idea is to keep this all from caving in. The only problem I would see here is the placement of the excavation material. It should be further away from the excavation itself, further back, because that does add a lot of load onto the earth that's adjacent, and you could have a collapse from that. So here's an idea called solder beams and lagging. You can see how these are placed in with an I-beam, and then the boards are placed between them. That's to help hold back and be able to allow being able to work around the excavation. So here are some sheet pile options, as they're called. You can see the timber sheet piling, how it's placed, or the steel sheet piling, which is more commonly used. These are driven vertically into the earth, and this precast concrete sheet piling as well, which is just, they're all the same system using 3 different types of materials: wood, metal, or concrete. All of them to shore up the excavation. Here's a slurry wall. These are used when there's a lot of liquid in the soil, a lot of water in the soil, and it shows how these are the steps are to lay it out, excavate the soil, then inject slurry to prevent collapse as excavation continues, and that's what the slurry is, or slurry walls. It can be a chemical. It's called, sometimes similar to what's called freezing the earth to keep back the water from coming through. It's done in a chemical manner, of course, with the freezing. Sometimes it's done actually by freezing through injections of methane and so on and so forth. Anyway, afterwards, once a slurry wall's been made, then you can cast concrete, and that eventually replaces the slurry mix. And you can see it's done in a number of steps. So you have slurry wall at one point, and then the further points away you begin casting. This goes through the different steps, one by one, of how it's accomplished from beginning to end, left to right. Tieback installation can be done by a rotary drill hole being made. That's where you insert these grout tendons, and then the tendons are stressed, and of course they create the anchor inside by expansion. So here's a little bit about bracing. One type is called cross slot, another called rackers and tiebacks. Now here's one way of helping to retain the earth. This screen system is actually, it works in the first stage, just the screen itself, to keep from some landslides, and then concrete is placed over that screening, and that pretty much shores up that whole type of situation there, that hillside from coming apart. So a retention system, of course, the type you use depends on your proximity to buildings, the type of soil, the water table level, and whether it's temporary or permanent, and of course somewhat on contractor preference. Cost is always the key consideration in contractor preference. Dewatering, a little bit about this. So dewatering is a process of moving water and or lowering the water table within a construction site. And the purpose is to provide a dry working platform. And it's typically required by different codes and specifications. So if the water table is above the working platform, you have what are the options? Well, keep water out, or that's keeping it out from the excavation altogether, or let the water in and remove it. That would be by pumping, or a combination of the two. So watertight barrier walls, when they're used, that's the keep water out type method, but the barrier must reach an impervious strata. So you have to, the lowest portion there is the impervious strata, and the idea is that the water can't go under the wall that you're building there, the wall that's used, the watertight barrier. If it doesn't reach to the impervious strata, which means, or layer, where water is not being able to pass from one side to the other, then it's useless. So some of these types are the slurry walls and sheeting with pumps. But again, they must resist the hydrostatic pressure, so that whatever's in the middle between the barrier, the excavation, has to be able to resist the pressure imposed by the surrounding earth. So types of foundations. The building consists of a superstructure, a substructure, and the foundations. And there are 2 types of foundations we talked about, shallow and deep. It depends on the load transfer, and is at deeper depths or shallower depths is dependent. The need for these 2 types are dependent on soil strength, groundwater conditions, foundation loads, and construction methods, and impact on the adjacent property. So shallow foundations are considered like this: column footings with or without tie grade beams, or individual or combined wall footings, slab on grades. Those are shallow foundations, or even a raft. Deep foundations are caissons, with or without sockets, end bearing or friction piles, all of those in the pile groups. And some of the zones of influence there are made of concrete, regular or site cast, or steel or wood. So here's that look at what we were talking about from a side view. The superstructure is the structure above. Substructure, think of that as maybe some lower garage levels. Superstructure being the building above, and then the foundation. And here you could see these were piers with that. Well, it's sometimes called a bell-shaped bottom, but they look triangular in this type of area, and or this type of drawing. And the idea is here these are dug very deeply. Then concrete is poured into those. This is not the pile-driven type, but the cast type, cast in place. So some primary factors affecting foundation choice: the subsurface soil, the groundwater conditions, and the structural requirements of the building itself. Some secondary factors: construction access, methods, and site conditions, so the site makes a difference. Environmental factors: building codes and regulations will make a difference. Impact on surrounding structures as well. You cannot undermine the foundations of adjoining structures that are very close to the site where you're building. The construction schedule itself, for speed altogether, and the construction risks. So shallow foundations, what are some of the requirements there? Well, suitable bearing capacity of the soil, and undisturbed soil or engineered fill needs to be used. Now the engineered fill is fill that is brought in from outside the job site and actually mixed to be a good type of soil that will support very well. So the basic types of configurations here are column footings or wall or strip footings. Another look at the shallow foundation here, what it looks like as it's dug out. You can see the earth adjacent, all cleaned out and built away from it. The footing is of course, with the rebar sticking out of it there from the top, and that on top of that will go the foundation wall. That's why that steel is placed right there in a straight line. So shallow foundations, get an idea of some what are called step strip footings. Here you could see how this could be used in stair construction. That's why also the grade beams that happen to be here on an angle to an actual figuring to a percentage of gradient. So here are some examples of shallow footings. SOG, meaning slab on grade. They have thickened edges, and that makes them what they are called eccentrically loaded footings. The difference there is everything is loaded on the edge, with the edge being thickened, not like a regular footing in a T-shape, which are concentrically loaded. So the loading on a concentric is fitting in the middle, to the middle of the footing, where the eccentrically loaded type is all on the edge of a footing. Then there are mat foundations, which are generally pretty analogous to the type of slab footings, except for they may be of a large amount. As you see the picture on the right lower, they can be. If you remember earlier, we saw a picture of all the H-beams, the steel beams being placed in the soil. That would be setting up a mat foundation. They could be spread out over a long distance and have these type of piers that they lay on. Then finally you have the floating mat foundation, which is isolated from the earth. And the idea with that is the floating mat, the amount of the weight of the soil displaced is equal to the weight of the foundation. So the soil bearing below, it has no worry of the capacity does not exceed of the new foundation, does not exceed that of the soil that was displaced. So you're using the same weight there, and then you have a lot less to worry about. So the deep foundations are where the caissons, those deep drilled and poured as we saw earlier. That's that bell-shaped base, as it's called sometimes. A socket caisson with a straight type bottom down below. The idea is it goes in. The difference in the color on the bottom is a different strata, mostly rock. With the bell shape, it's sitting on that type of rock, and it's pretty much distributing the load. That's why you have that wider portion down the bottom. But the obvious difference in a socket caisson is it's been drilled. You've drilled into the rock, and you're actually pinning, like driving a pin or a nail into a piece of wood. You're actually, that caisson becomes part of the rock at the lower level. And one is an end bearing pile, and the other is a friction pile. That's commonly used in the pile driving. A lot of times it was wood in the old days. Now mostly you see I-beams being pile driven. Very quick. Don't have to wait for concrete to dry and to cure. That's the reason, and they're becoming very popular once again. So here's a little bit about the caisson installation sequence. First, a hole is drilled with a large drill rig. Then a casing is installed. Mostly, sometimes it's done in the rough, poured rough in there. It depends on the soil type. But you can think of that as those sauna tubes or cardboard tubes type thing. Here you may have the bell or tip enlargement. That's that bell-shaped bottom. The bottom is inspected and tested. And after that, the reinforcement is placed, the metal and rebar. Finally, the concrete placement and the casing removal in many cases. Here's a look at the equipment. There's a large rig drilling a hole. Could be 30, 40, 50, 100 feet deep with this kind of a setup very easily. This may be a high-rise building, pretty big building, obviously. So driven piles, of course, are two basic types of piles: the end-bearing pile, the point loading, and the friction pile, where the load is transferred by friction resistance between the pile and the earth. You can see one sits on the rock at the bottom, the heavier. It's usually rock, but down below that it would be on that darker portion in the bottom of the illustration, whereas a friction pile depends on the earth around it, just holding it into place. So obviously one can support much more than the other, and that would be the end-bearing pile. Most of the end-bearing pile is doing what they call point loading, and that's just transferring all the weight to that bedrock or rock down below. So here are some of the materials used in piles. Steel, like I said, the I-beam, or the H-pile they call it. Steel pipe can be used. Concrete, site cast or precast. Wooden timbers, that was the old way. And even a composite. So a little thing about the Nashville Coliseum. It's 67,000 seat sports Coliseum in Nashville. This facility had deep foundations. 3,500 different driven piles. 12 by 53 H piles with an end bearing, and each pile length varied between 25 and 75 feet. The reason for that is hitting the rock down below, you go into it pretty much goes until they know the drill point to where they've hit in rock, and it varies in the depth for each hole driven. So they used 3 pile drivers with diesel powered hammers. The driving rate was 20 to 25 piles per day per rig, which is a high amount, very quick. And the driving tolerance, meaning missing their mark, was between 3 and 6 inches. And here's what it looks like close up, this Coliseum and all their pilings in place. You can see there's many pilings that were placed in a grid fashion so that another type of foundation could be cast around it. Take a look at how that looks in the close-up. These are the H-beams, and they're all placed close together. So here's the precast concrete piles. Precast concrete is stressed, has a stress test of much higher, usually 5,000 psi and above, compared to the minimum of concrete that's cast in place, which could be as low as 2,500 psf. So here's how it looks on the side view for the site cast concrete piles. You can see the cased piles, how they look as compared to the uncased piles. Here we'll take a look at some of the precautions to be taken and the terminology. So one is called seismic base isolation. It's used in the seismic areas. Another one is underpinning, and that's used when you're required to carry out repairs to existing buildings or to add some changes in the foundations. That's actually giving some more support, adding support. Sometimes holes are drilled in concrete, injected. There's different ways of doing it, but that's underpinning. Another way is sometimes you have to build retaining walls to hold the soil back from caving in, to prevent types of failures such as overturning, sliding, and undermining. All these need to be avoided, and these non-reinforced and or reinforced cantilevered retaining walls are put in place, where drainage behind the wall is placed behind the wall to eliminate piping of water in the soil. Another item here is waterproofing, which is using waterproof membranes, sometimes an asphalt coating, and of course the drainage around the foundation with perforated pipes. Now the basement insulation, which is another item of foundations, where polystyrene or glass fiber boards are placed on the outside or inside with drainage mats. Another item of consideration is frost protection through protective coatings and plastic foam insulation. And the most important is when you come to the end of the process to backfill against foundations with the properly draining soils. So let's take a look at these one by one. Seismic base isolation. How is this accomplished? You could see there's these special connectors here down at that are placed down at ground level between the building and the that's in that case that would be a cast in place caisson. Retaining walls. Here are the items we don't want to have: the overturning, or sliding, or the undermining. Any of those three to happen. So we do certain things here. And we're going to look at some of the other terms used here for retaining walls, which is wall fracture, overturning, sliding, and undermining. Again, and let's look at some of the preventive methods. So here's the design elements. You could put crushed stone behind the retaining wall as a drainage layer, and then have weep joints below. What that will do is reduce the hydrostatic pressure. It allows the water and the earth to pass through the wall. You see a lot of these walls, even all the way up, they actually place pipes in them, so it's allowing the water to always go through the earth. If it soaks into the earth, it doesn't just stay there and build up extra weight. The water adds a lot of weight to the soil that's being retained. Instead, it can just pass through the wall and weep out or just drip out in different areas. So again, here's the idea: the hydrostatic pressure. For all three types of failure, this is one of the items that you can use, and of course it works with to help with the overturning. You could also do cantilevered footing and reinforcing. Now the cantilevered footing is down below. As you see, the footing is offset, and there's a key placed in there. It's called like a key to prevent the sliding. So that's another item. Those are all three of those items working together to prevent the three different situations we saw previously. The key keeps it in place. The cantilever helps with to help prevent failure as well. So waterproofing. Structures below ground are subject to penetration of groundwater, and it's more extreme, of course, if your foundation's below the water table. So there's two basic approaches to waterproofing, and that's waterproofing membranes or drainage, and generally those are both used in tandem. So waterproofing membranes. What type of materials? Well, the liquid or sheet type, plastic, asphaltic, synthetic rubber. Those are all being allowed to be used. Then you have the coatings that come in almost like a 5-gallon, as little as a 5-gallon bucket or even a gallon, and they're asphaltic based. Those are the type that you actually brush onto the foundation wall. Another one is cementitious plasters and admixtures, those have been traditionally used in some of the oldest types, using Portland cement and as a mixture. It's often, there's another word for it called parging, and what you do is make a mixture that's just waterproof and used to trowel it onto the foundation. And there's even this item of bentonite clay being one of the oldest method, really the oldest method being used. Is clay is pretty much impervious to water movement, so you can actually coat the foundation with this clay mixture. Then there's a few other ideas that you might have, which is called a protection board or a water stop. And just to say, the way these are measured, of course, by square foot, because of the foundation wall being figured, it's almost like painting on a wall. And the other ones, the liquids or the sheets of plastics, synthetic rubber, those are measured in mils, which is the thickness, and you'll see that in the requirements given by the building department or the local or the code or the International Code Council, requiring the thickness of how many mils before it can be considered a waterproof membrane. Some more on the drainage methods. You could see the oldest one of the tried and true is a stone and perforated pipe down the bottom that goes right around the perimeter of the footing. So there's also the other type of a drainage mat and perforated pipe. So here's a drainage map and what it looks like inside, in reality, on the site. Damp proofing. This was you can see a liquid asphaltic was placed, which is a brush-on tar type, rolled-on type, or sprayed-on. That's almost like the roofs. The same type of method used, where asphaltic layer. It's not an effective barrier so much for water, especially water under pressure. It's called damp proofing for that reason. It's not waterproofing, but will prevent ground moisture from migrating through a wall. And it was typically used in conjunction with a drainage pipe. You can see that something's placed over it to protect it. Always that way, because the backfill in the old days would destroy or make little dents in that. It's almost like a painted-on finish. So the idea is to protect that. That's usually what that's for. It could be any type of material. Usually use the polystyrene, some type of foam type that works as an insulation barrier as well. We're going to wrap up this module on foundations in a few more slides here, looking at foundation design for optimal cost, which is controlled by many factors. And we could say that integrated, and for the first one, integrated decision making and functioning of architects, structural engineers, and foundation engineers have the first input in design and at optimal cost. And then the site factors start to follow in, like building below the water table, which ends up being costly and sometimes is damaging to the building. Building too close to an existing structure is to be avoided because of the extra cost of pinning, and any digging activity on either sites will affect one on another and can lead to costly repairs to the neighboring site, obviously. Some column or load bearing becoming more than what can be supported by a shallow foundation. So deep foundations, as a rule of thumb, are expensive, much more expensive. And if building or structure can be lightweight and designed to be lightweight, like wood construction, rather than being a concrete masonry unit type construction, which weighs much more, then those are considerations that can help mitigate the cost factors there with the type of foundation you're using. One last thing here is the uncertainties can be avoided by using larger factors of safety in the design of foundations over soils, so the safety factor comes into play as well in reducing, obviously, some costs of different items there. Thank you for viewing.